In this lesson, we're going to talk about volume and see how integrals can help us with volume. So the volumes that we'll be looking at are called volumes of revolution. So as I'm sitting here making this video in my kitchen, we got some volumes in front of me here. Let me snap some pictures. All right, here is a candle, and it's solid, and it's got some kind of curve here. And that curve, let's see, this curve right here has been rotated around an axis. And it's spun around. And when we spin it around, we get this candle shape here. So this glass curved container. So yeah, we got a couple more here. Here's a drinking glass that looks like a nice straight line here. That's not a very nice straight line. Okay, let's try a nice straight line down here. And if we take that and we rotate it around some center axis. Okay, so if we rotate this guy, then it's going to spin around and it's going to make the outside of this glass. Okay, so we get these rings of rotation kind of going around here. Okay, and we get this solid surface, and we can talk about the volume of that surface. Now this one is called a frustum of a cone. It's a cone like with a little bit of it cut off, like this little bit down here was cut off. Okay, this one is more of a hyperbola or a parabola that is rotated. And then, here's an interesting one. Here's a salt shaker. Looks like a giant salt shaker because it's zoomed in there. And so this one's not a, if we look at the edge of it here, it's not a mathematical shape. I don't think I could come up with an equation for that, like the other one was a line or a parabola kind of thing. So, but this one, if we take this shape, this little squiggly shape, and we rotate it around, we spin it. We were to spin it around an axis. Okay, the center. Think if we have like a center line here. So if we have a center line and we spin this around that axis, then we'd get this shape. Okay, that kind of thing. So, all right. So these are called solids of revolution. Okay, something that can be spun. All right. Can you picture these here? Okay. So if we take these two-dimensional drawings and we spin them, what would a three-dimensional picture look like? If we spin them around the line, which we call the axis of revolution. Well, can you tell what this one's going to be? If we rotate this rectangle around, it's going to make a cylinder, right? So when we spin this rectangle, just some dotted lines back there, maybe. There we go. We get this solid of revolution. Now if we take the same rectangle and we rotate it around a different edge, what do we get then? Well, we're going to get another cylinder. It's just going to be a little bit longer. Or actually it's going to be kind of, we might say it's kind of short. This is more like a can of tuna. Than a soda can. Okay. So we get this long skin, and the radius would be here. That would be the radius. And this would be the height. Back on this one, the height is the long side, and the radius is the short side. Okay? So depending on where the axis is, we get different shapes there. What if we spin around the middle axis? Well, if we spin it, imagine rotating this around a stick or something like that. Well, it's going to spin around, and it's going to carve out this disc there, okay? So we get these cylinders, and now the radius here would be half of that height right there, and the height would be that short distance. Okay, so great. Well, what if we spin these ones? If we have a triangle, we spin that. Well, let's see. If we spin this around, it's going to go kind of like this. It's going to make a cone, right? Okay. So if we spin that, that'll be a cone. This will be the radius. Okay, and this would be the height of the cone. Okay. If we take a half circle and spin that around, well, this guy's going to kind of spin around to here. And this guy's going to spin around to here. So on and so forth. And we're going to get a sphere. Okay. And they kind of rotate around this way. Okay. So different shapes give us different two-dimensional shapes, give us different three-dimensional solids, okay? So, and it depends on where that axis of revolution is, all right? So that's an important word there, the axis of revolution. Okay? Great. Now, so the shapes we're going to focus on are rectangles, because we're going to break things into rectangles. Remember when we were finding integrals? An integral is the area under a curve, and we break things into rectangles. Well, now we're going to break things into rectangles, and we're going to revolve them, all right? So every rectangle has a width and a radius here. This is going to be a radius because when we spin this around, we're going to get this disc, okay? And the way we can find that volume of the disc, okay, the volume of a disc or a cylinder is the area of the disc times the width, okay? Or you might remember from geometry, volume equals the base area times the height, okay? And that's going to be given to us by pi r squared, where r is the height of this disc, times w. So let's find some volumes here. So here we have a rectangle, and this is the function r of x equals 4, all right? So r of x equals 4 is a horizontal line. Why are you not working? Here we go. R of x equals 4. All right. So that's this line right here. This is the axes. Maybe kind of hard to see. There's x-axis, there's the y-axis, and we're going to revolve this around the x-axis. So if we spin this around the x-axis, it's going to give us this kind of skinny disc, this cylinder here. Hopefully you can picture that there when we can spin it around. And so the volume here is going to be pi r squared w. And so the radius is 4. And the width is this distance here. So 2. You could also call that the area of the base times the height. You can think of it. All right. So this is going to be 32 pi. There's our volume. And we don't necessarily have units here where we're talking about in the coordinate plane. So in many cases we don't have units. So all right, so now let's take this a step further. So that was a rectangle. That's nice. But when we have a curve, like let's say we want to take this curve here, we want to rotate this curve around the x-axis, okay? So when we rotate that or revolve that around the x-axis, we're going to get a more complex shape like this blue thing here, okay? This funnel-looking thing here. And so if we want to find the volume of this funnel-looking thing, then we're going to break it up into discs. We call these representative disks. And so we're going to start by finding one of these disks, and then we're going to break it up into several disks. So we're going to say if we could find the volume of these disks and add them up, then we get a pretty good approximation of this funny looking funnel, the volume of the funnel. So this is called the disk method. That's a good name for it, since we're talking about these disks. And then we want these disks to get thinner and thinner, right? Can you see how that works? So if these disks were really thin, right now this is kind of a bad approximation here, right? This brown looking stair-steppy thing doesn't look a whole lot like this blue funnel, this blue solid. But when these disks get real thin, then this is going to start to get really close to that funnel. And eventually, when they're infinitely thin, then we have the perfect blue solid of revolution. All right, so that's the idea. So we want the width, the delta x, to go to 0. Does this sound familiar? Well, yeah, of course, because this is how we found areas with integrals. So we found that we took rectangles and we made these rectangles smaller and smaller. Well, now each rectangle represents a disk. So the volume of the solid is going to be the limit as x goes to 0 of pi times the radius squared. So remember each of these rectangles here. So the volume here is pi times big R squared times the width, or in this case, times delta x. So with that, we have this guy. So we're going to take the volume of each of them. So we're going to sum them. That's this. This is the sum of our disks. And so we've got each of these disks. We've got pi times the radius of the first disk squared times delta x, plus pi times the radius of the second disk squared times delta x, plus pi times the radius of the third disk. You get the idea. Times delta x. And so if all these delta x's are the same, then we can factor out pi. There's pi in all of these here, all right? And there's a delta x in all of these. We're going to keep that there. And these are the different radiuses. So the radiuses are determined by the function f of x, right? So whatever the height of the f of x is at some given x value, some x sub I, then that's going to be the disk. So this is all of these terms added up. Well, if we pull out this pi, then this looks real familiar. This is just the formal definition of an integral from a to b. And so we can write that as pi times the integral of a to b of rx squared. Rx is the function. So I put f of x here. I guess I should have put r of x. All right, great. So this is called the disk method. And we can revolve this either horizontally. And if we revolve it horizontally, then that gives us like that funnel up above there. Then that gives us a function that's revolved around the x-axis. So that's around the x-axis. If we revolve it vertically, then that's around the y-axis. And so we'll have to treat those differently. So if we want to revolve it around vertically, we got to have a function of y. All right. So let's try a couple. Okay, so we want to find the volume of a solid formed by the region bounded by the graph f of x equals a square root of sine x. Well, that's kind of an interesting graph. So f of x equals the square root of sine x is this guy right here. Kind of this arch looking thing. And when we revolve that, we get this little looking football, or it almost looks like a pill of some sort. Looks like it got cut off also somehow. So Yeah, so it's actually going to be down here also. So we get this shape. Seems like a pretty useful shape. And it kind of looks like I don't know, NyQuil or something like that. If you're sick, you need some NyQuil, and you take one of those gel little pills there. Anyways, so what we're going to do is we're going to rotate this region here, right? And so we got to think about each rectangle here. And so we're going to rotate this. So this is called our representative rectangle. And as we do each of these, we're going to look at different types of volumes. We have the representative rectangle. And the reason why that's useful to draw here is because it reminds us that, okay, this is a little slice of the pie, a little slice of the integral, right? So remember your Riemann sums where we broke this into a whole bunch of rectangles. If we were revolving this around the y-axis, then we would need to think about a whole different rectangle. And that would get a little more complicated. We'd be looking at rectangles like this. And so that would be a different story. So this is the rectangle we're looking at. So as we revolve it this way around this x-axis, this rectangle is going to become a disk. And so we're just going to have a whole bunch of disks. So let's go get to our integral. So our volume is going to be pi times radius squared, or in this case, the sum of a whole bunch of radius squareds. And the radius is determined by the function. So the function squared dx. So, and we're going to add them all up. Well, integral is a sum. So we're going to add up all the radius squareds. The radius is determined by the function. And we're going from 0 to pi because of this thing right here. All right. So now, all right, but this is an important thing to write first. Pi times the integral of f of x squared dx. I haven't gotten into any specifics because right there you should see that this is pi r squared times the height and times the width. And the width is dx. It's that dx that's infinitely thin. All right, so that's what an integral is. So the width becomes the dx. And the dx is an infinitesimal. So they're infinitely thin slices. Okay. So let's go ahead and substitute now. So we can say this is pi times the integral from 0 to pi of, f of x. F of x is the square root of sine x squared dx. And isn't that nice? These sines cancel out, or the squares cancel out, that is. And so this is just sine x dx. And we know that the integral of sine is negative cosine. And we're going to evaluate that from 0 to pi. Don't forget this pi out here, and don't get that mixed up with this pi. These are our bounds. This is the pi that comes from the formula for volume of a cylinder. So this is pi times, plug in pi here, cosine of pi, so negative cosine of pi. So careful with that negative. So it's negative, and the cosine of pi is negative 1 minus negative, got a whole bunch of negatives here. Gotta be careful with the parentheses. Cosine of 0 is 1. All right, I think we got it there. So if we evaluate this, we get negative, this is positive 1 plus 1, and so that is 2 pi. So the volume is 2 pi. And if we had units, it would be cubed here. So 2 pi cube units. that's our volume of this funny looking football pill shape. So that's revolving around an x-axis. So we'll see some in our assignment where we're revolving around a y-axis. The difference there is that we're going to need this function here. This is y, well, let's say this. Yeah, this is y equals x squared. Now if we want to revolve this around the y-axis to get this kind of parabolic shape here, this bowl kind of shape, okay, then we would need to integrate this with y. So this, if we want to get this volume of this solid here, then we would need to have a volume equals pi times the integral of f of y dy from a to b. So we want to do that. So if you're going to revolve y equals x squared around the y-axis, then we need to change this into x equals the square root of y. All right, so we won't do that whole problem right now. We've kind of almost done it there, but now we can plug this into here and solve that. So if we're going from, well, let's go ahead and say we're going from -2 to 2. But we've got to be careful now because we are integrating with respect to y, and y is going from 0 when x is 2, then this is going to 4. So since our variable of integration is y, we're going to use that 0 and 4. So the volume would be pi times the integral from 0 to 4 of the square root of y, oh, forgot my squared dy. And that cleans up pretty nicely. So this is going to be the integral of y from 0 to 4 dy. And so that's just going to be 4, and then we get y squared over 2 evaluated from 0 to 4. And that's going to be 4 times 4 squared over 2 minus 0 squared over 2. And that's obviously 0. And so this is 16, that's 8. And so we have 8 times 4, and that would give us 32. So the volume is 32 for that bowl-looking shape there. All right. But again, if we want to revolve around the y-axis, we need to have a function of y to use the disk method. Well, let's look at a version of the disk method now called the washer method. So when we have something that is not right on the axis, then when we spin that, it's going to have a hole. It's going to be a donut or a Cheerio. And it's going to have or we call it a washer, like a metal washer. Here's a metal washer, if you're not familiar with them. Something goes around a bolt and with a nut. Anyways, so that's why we call it a washer. A little more interesting to think of it as a Cheerio or a donut there. Okay, so now it's important here. Oh, my washer is not going with us. So it's important to remember that when we're thinking about these different methods, we want to think about the two-dimensional problem, the flat version, like the disk. The disk came from the circle, right? So we know the circle, the area of a circle is pi r squared. So if you take that circle and you make it into a disk or a cylinder, volume equals pi r squared h, pi r squared times this height, right? Okay. And so that gave us the formula for our integral, the volume of a revolution of a disk volume of revolution, let's make the V, is going to be pi times the sum of the f of x's, which are like all the radiuses, squared. All right. So pi r squared, that's where that comes from. Okay. Well, when we've got a hole in something, we have a washer. Okay. Or the name for this in a flat shape is actually called an annulus. So an annulus is a circle with a hole in it. Now, how would you find the area of this disc, or this annulus? You would need to figure out the radius of the inside, and you would need to figure out the radius of the outside circle. And so the area of this annulus would be pi, the big circle, pi times the big R squared. We'll call that big R. And we would subtract pi times the little r squared. See that? So if the big radius here, the big radius was 10, we do pi times 10 squared minus pi times 2 squared, or whatever that small radius is. Okay? Or another way to write this is to factor out the pi, and we got big R squared minus little r squared. There are two radiuses. Well, if we make this into a washer, kind of three-dimensional like, so we've got a hole in the washer, dear Liza. Okay, so we've got a hole in this thing. Well, the volume is going to be that pi r squared minus r squared, that's the area of the base, times the height. Okay? Well, when we take that into our integral situation, we can see this. Okay? We're going to find the volume of all these disks, and we're going to have big R squared minus little r squared, but these are functions, because remember, this is going to change, as we'll see. So the outside radius minus the inside radius squared dx from a to b times pi. Okay, so that's what's coming, and that should look like an annulus now after that little discussion. All right, so here's an example. So we want to take this shape here, and we want to revolve this around the x-axis, the region between y equals square root of x and y equals x squared. So the region between these, the area between these, we've looked at. Here's the region in between. It looks kind of like a leaf or a flower petal or something like that, all right? So this is between y equals the square root of x. So we need to know something about our graphs. Y equals the square root of x looks like this, right? And y equals x squared looks something like this. We're very familiar with that one. All right, so those two intersect right here. Okay, let me draw those back in. That might help. So there's y equals x squared, and that's y equals the square root of x. And so we're going to spin this around the x-axis, and when we spin this around the x-axis, we're going to get an interesting looking shape here. Okay, it's going to kind of be a bowl. The inside of the bowl is going to kind of bulge here. All right, so this would not, I don't know, it would not be a very good salad bowl. It's kind of a funnel on the inside, a bowl on the outside, and kind of a funnel on the inside. So, anyways, interesting looking shape here. We want to find the volume of this, okay? All right, so how are we going to do that? Well, to do that, we're going to imagine this representative rectangle, okay? So we always break it down to this representative rectangle. This helps us keep our all variables straight. So this rectangle is like one slice. Think of it kind of as the Riemann sum, right? And so when we take this rectangle and we revolve this around the x-axis, okay, that part's going to spin there. That part's going to spin there. Okay? And then the outside of it going to have a lot going on here. So the outside of this is going to sweep out a big, circle. Okay? And I won't even draw the rest of that. So we get this analysis right here. This is kind of the side of that washer. Okay? So that one rectangle makes one washer, okay? So what's going to be the outside? Well, the outside is coming from this one. This is the outside curve. Or it's doing the outside of that bowl. And then the inside is coming from this. So the inside is coming from y equals x squared. And the outside is coming from y equals the square root of x. Okay? And the outside is going to be our big R. Okay? So this is big R. And the inside here is little r. Okay? And to kind of think of that, to understand that better, think of this analysis, or this little washer, that one slice. All right, so let's put it all together. So using this formula here, volume equals pi times the integral of big R squared minus little r squared. Okay, so we've got volume equals pi times the integral. Okay, now what are we integrating from? We're going from 0, the x coordinate, to 1. All right, those are the x's. We're changing. Each rectangle is going to be determined by where we're at on the x's. Okay, and these rectangles that get infinitely thin. So we have big R squared minus little r squared dx. Okay. And there is our formula. Now let's plug in what we have so far. Pi times integral going from 0 to 1. Okay. And the big R squared was the outside. That's the square root of x squared minus little r, which is x squared squared. So we're just putting the function in there is all I did there. And so let's do some cleanup. This equals the integral from 0 to 1 of x minus x to the 4th dx. That seems doable. And so we have pi times, take the antiderivative, x squared over 2 minus x to the 5th over 5. From 0 to 1. Evaluate that from 0 to 1. And so we have pi. Now let's be real careful here. Well, the zeros are going to cancel out. I guess we don't have to be that careful, but plug in the ones. And that gives us 1/2 minus 1/5. Minus, and then you're going to have 0 halves. Minus 0/5. That's easy enough. And so this is just, let's see, 1/2. So this is 5/10 minus 2/10. That's 3/10. 3/10 pi. There you have it. Okay. So we found the volume of that funny little shape, this area that would be kind of in between, all wrapped around here. And the volume is 3/10 pi. All right, so that's the idea of the washer method and the disk method. Okay, so to finish this off here, the disk method gave us pi times the integral of f of x squared. And here we're going to have the volume of revolution is going to be pi times the integral from a to b of big R squared. I'll write this way, big R of x squared minus little r of x squared dx. All right, and again, if you remember the two-dimensional picture and the two-dimensional formula that goes with that picture, that leads pi r squared. Well, that's pi times f of x squared, and we got to add up all the f of x's. Here we have pi, the area here is pi big R squared minus pi little r squared. Factor out the pi. And the volume version of that here. So we have pi times the integral of big R squared minus little r squared, but r and r are functions. Okay? So there you have it. I'll do another video for the last part, which is area of cross sections, known cross sections, making three-dimensional solids out of known cross sections. That's kind of a different technique. So take this, work on the assignment, and then we'll continue on. The last part of the assignment will be these known cross sections, and we'll come back to another video for that. Keep up the good work.